right, into section number 4 now. And this is the first time that we're going to be doing a design case study activity. We're going to be designing enterprise connectivity. In this design challenge, the goal of this design lab is to learn how to take a customer requirement into consideration and design a network as a result of customer migration plans, in this particular case, from RIP version 2 to Ospf. We're working with an IT company and our customer, Acoustics Limited. We have been hired to design the expansion of this network and at the same time to migrate the network from RIP version 2 to Ospf. The customer is a large enterprise company with many branches with a primary and redundant links. Each recently, after connecting many more branches to the network, the company started to experience intermittent network failures and slow convergence. Primarily because probably RIP version 2 just simply doesn't scale to the size of the network that we need. So we can see our overall topology here. All right. Here are some of the customer requirements. The customer networks connect many branches in a classic hub and spoke topology. Each of the branch location has a primary and a backup link to the company headquarters. All the primary links are Metro Ethernet with a separate interface for each branch location. The backup links are implemented via a separate physical infrastructure that uses GRE tunnels across the public internet. Pretty common, actually, to do a private versus a service provider versus a customer-managed VPN over a public domain. Most of the branches are implemented using a similar equipment and topology except for branch 3, which has an EIGRP cloud that is a legacy solution from a past merger. Mutual redistribution between RIP version 2 and EIGRP occurs at that particular point. So is that in the diagram here? Yes, right here. They're talking about branch 3. We have a RIP version 2 domain, but we also have EIGRP being redistributed into RIP. All right. I don't know that that really makes much of a difference. RIP pretty much treats redistributed routes just like it treats internal RIP routes, but we're making a mention of that. Okay. The customer does not want to migrate the EIGRP part of the network, so it should be left in its current form. The customer informed you that extended downtime in the EIGRP cloud during the migration is not an issue. Apart from the EIGRP segment, the network is operating using RIP version 2 as the IGP. However, RIP version 2 network was designed and implemented poorly. Therefore, the customer is not happy with the performance of the routing protocol. Is there actually a good way to implement RIP? I don't know. I don't think so. Of the routing protocol and wants to migrate the network to another protocol. As the network has been growing lately, the customer started experiencing more and more intermittent network failures and slow convergence times at the time, and at times primary link failures. By assessing the situation, you notice that although the branch IP routes can be summarized, they are not summarized at this point. Also, the customer is planning the rollout of a new VoIP service, and this service requires better network performance, mainly in convergence times, to improve significantly. Certainly using a classic distance vector routing protocol is not the best choice in that particular case. RIP version 2 is a very, very slow converging routing protocol. Because the network comprises devices from several vendors, the customer is considering a migration to a standards-based link state protocol. Well, we only have 2 of those. That has a wide vendor support and good documentation. Well, that pretty much limits us to Ospf in this particular case. The customer is relying on your expertise to choose the protocol and implement the migration with the least possible downtime, Note that some of the routers in the branches are low-end routers and might not support service provider-oriented routing protocols. So again, they're trying to kind of get us to get to this idea that we're going to use Ospf as our routing protocol. Lastly, the customer does not want to use BGP because the customer would need to buy expensive licenses for their existing routers. So in this particular design task, we need to take a look at, well, how do we choose the appropriate routing protocol? How do we design the backbone area, the spoke areas? We have that one special use case where we have EIGRP being redistributed, Ospf summarization points. What are the RIP version 2 to Ospf migration steps? How do we handle route redistribution? And then how do we finally get rid of RIP version 2 after we complete the migration? And how do we account for future growth? These are all the questions we kind of ask ourselves in this particular case. So the first task is to choose a routing protocol. In this task, we need to choose the interior routing protocol for migrating from the network of RIP version 2. And we want to make sure that we're going into a multi-vendor environment. BGP, because it is standards-based. EIGRP, because EIGRP is already in the network. Ospf, because it's standard-based. Or ISIS, because it is a link state protocol. The solution, of course, was to choose Ospf based on the criteria that was outlined. We don't have routers that support service provider level routing. We want to use an open standard routing protocol, so EIGRP is out. They already specified that they don't want to use BGP because of licensing issues. BGP would not really be a good choice anyway, right? BGP is not designed to be an IGP routing protocol. It is an exterior gateway protocol, so it's supposed to be used to route between autonomous systems, not to route internally within our autonomous systems. So the protocol that we should choose in our design to improve the overall network operations and convergence is Ospf. Ospf is a standards-based link state routing protocol. It has a vast install base, lots and lots of documentation. It is proven to work well between devices from different vendors. BGP is out of the question in this case because the customer's current equipment doesn't support BGP, and buying extra licenses would be too expensive. ISIS does fulfill most of the requirements, but it was actually ruled out as a protocol because it's mainly used in service provider environments, and support availability and install base in the enterprise network is not as good as it is with Ospf. All right. So that's what we chose based on that. All right. So the next question we ask ourselves is, how do we do the, did I skip something here? No. All right. How do we do the backbone area design? We need to analyze which routers are going to participate in the backbone area. Which routers are going to participate in area 0? Is it only going to be the HQ routers, or is it going to be the branch routers as well? Now, if I'm looking at this topology and I'm trying to consider how I want to do this, we essentially have two options. Well, actually, we have three options. We could simply implement a flat design, but I think we can kind of rule out that option because they did say that summarization is certainly a possibility from the branch locations. So it appears as though, even though they implemented RIP poorly, they at least allocated their IP addresses accurately, and all of the IP addresses are, identified or installed correctly in a hierarchical fashion, contiguous address blocks at the branch locations. So in order for us to be able to summarize in Ospf, we can't run a single area design. So that's going to limit or eliminate that possibility of running a flat design in OSPF. We also know that we only have the ability to summarize on an area border router, an ABR. And if we want to summarize to HQ, those summaries would have to be created at the branch. So for that reason, the company HQ routers most likely would have to extend, we would have to extend area 0 down to the branch locations, meaning that in this particular case, we would have essentially area 0 that would look like this, and then each of these would be different areas in this particular case. That would make each of those branch routers ABRs, and we could apply the summarization and summarize into the backbone from those branch locations based on that design. If I didn't choose that design, it would make it extremely difficult to do summarization. If I said, you know what, let's go ahead and, well, actually, I don't even know how we would really do that. I was going to say just make the company HQ routers area 0 and extend the non-backbone areas to the HQ router. I guess if we had virtual circuits, we could do it. But based on the physical topology, the red lines here, the red links, it looks like we wouldn't have that particular option in this case. So the questions, which areas are going to be area 0? Which routers are going to be participating in the non-backbone routers? And it says here, how should we ensure that the backup links are less desirable than the primary links as well? What mechanism will we use? Well, that's interesting. We could do that by manipulating metric values. We could do that by essentially making those backup links look less favorable in OSPF by adjusting cost values or adjusting parameters that would result in the calculation of cost. All the routers in the HQ and the border routers and branches will be part of the backbone area. Makes sense. Because that's the only way, like I said, that we would be able to ensure that we could do the summarization at the branch locations and send those summary routes into the backbone. OSPF places interfaces into areas, so the branch routers will only place the interfaces facing the headquarters into area 0. The backbone area should be extended all the way to the branches because otherwise you would end up with many areas on your hub routers. Performance can be negatively affected by this design. You will include links from both the primary and the backup branch routers to area 0. You will make the backup links less desirable than the primary links by defining a higher OSPF link cost for the backup links so that the GRE tunnels will appear to be more costly. All right, I agree with that completely. That makes perfect sense. I don't know exactly how you would be able to extend those non-backbone areas based on this topology, how we would extend our non-backbone areas to the HQ location, given that HQ only has one WAN connection and one internet connection. Because an interface can only be a member of one area. So we would either have to create logical sub-interfaces and have different subnets, which works fine in the WAN scenario if we have a technology in the WAN that supports that. Doesn't really work very well in the internet-based scenario. Although the GRE tunnels that are created over the internet we could have multiple tunnels, I guess, to each of the branch locations for each of the areas. So, well, we would have that anyway. So that would work on the internet side. But again, they don't even mention it in their solution here, the idea of summarization. And in order for us to be able to summarize, we have to have ABRs. And if the ABRs are all back at the headquarters location, it's not the best place to provide that summarization. We should do it at the branch location before the information gets over to the headquarters. All right. All right. Determine the spoke area design. So we're going to analyze the spoke area design for the branches. How will you design the spokes for the network? Will you extend area 0 all the way? Will you create extra areas? I don't think in this case that we would have to create extra areas. The spokes are going to get placed into area 0, into different areas because area 0 won't scale. I think what they're talking about in this particular case is that they're talking about the LAN side of the spokes, right? Not just the WAN side, but the LAN side. We have potentially multiple routers in each of these branch locations. We only see a couple of extra ones, but who knows? Maybe there's 10 or 20 different routers at these branch locations. And they're, in essence, talking about extending area 0 all the way out to the edge of the network, meaning that basically everything would be area 0. If there are extra areas, what type of area do we want to create? Stubby, totally stubby, normal areas, not so stubby areas. This gets a little bit more complicated. We could choose between stubby or totally stubby, but we do have redundant connections. So it is something that we have to consider. Now, we're not load balancing over those connections. We're only using a single egress point. The WAN is the primary egress point, and the internet connection is the secondary egress point. So actually, it would be entirely feasible in this case, using the GRE as a backup and the WAN as a primary, to go ahead and configure those branch locations as special area types. Remember, we have an option of doing stub or totally stubby, except for branch 3. Branch 3 has an ASBR, or will have an ASBR in it, because they said they didn't want to get rid of the EIGRP domain. So we are going to have an ASBR in branch 3, which means that we can't configure that as a stub or totally stubby. That would have to be a not so stubby area. But it's definitely something that we could do because we're not load balancing. We're not trying to utilize both of those links. One link is a primary and one link is a backup. Let's see what they say here. The spokes will be placed in areas because area 0 cannot grow to these scales. There would be too many devices in the backbone area, and you get no benefits with the stub area default routing and summarization at the ABRs. Right, if everything is in area 0, you can't run special area types and you can't do summarization. Regarding the area type selection, you can choose between stubby and totally stubby. However, because the branches do not have any other exits out of the area except the headquarters, it is safe to deploy totally stubby areas that require less resources. The only difference between stub and totally stubby is whether or not type 3 LSAs are allowed into the area. And type 3 LSAs would be all of the LSAs that we would learn from area 0. In either case, whether it's stub or totally stubby, a default route is going to be sent into the area. And if that default route is preferred, then we'll choose that path. Remember, we do have the option. I don't know if you recall this from your OSPF days when you were learning about OSPF, but we do have the option of setting the seed metric for those external default routes that are being injected automatically by the ABR when we create a special area type. So we can create somewhat of a preference as to which path we're going to use for that default route, which plays very well into this scenario because the WAN should be the primary path and the internet-based GRE WAN should be the secondary path. They do not mention here whether or not we should do something special for branch 3. But I think that's in the next topic here, the special use case, if you will. Let's see if that's next. Yes, special use case. For branch 3, what do we do for branch 3? What type of area should we implement for branch 3? How is branch 3 different? Well, it's different because we're doing redistribution in branch 3, which means that we're going to have an ASBR. There's no concept of ASBR in RIP. RIP just accepts routes from another routing domain through a basic redistribution process. But because we are configuring the other branches as special area types, we would have to consider branch 3 differently. From an Ospf standpoint, why is branch 3 specific and differs from the other stub areas in our design? If the area is a totally stubby area like the other areas, how will we inform the core about the EIGRP networks? We actually wouldn't. In fact, those external networks that are being injected by that ASBR would be ignored because they would be coming in as type 5s. And type 5s are not allowed in a stubby or totally stubby area. In fact, type 5s are not allowed in any special area type. So we would have to configure that area as a not so stubby area, which provides, or a totally not so stubby. I would argue totally not so stubby because, again, there's no reason to see the type 3 LSAs coming in. All right, because we want to inject the default route. By the way, NSSA doesn't do that by default. NSSA is the only special area type that doesn't automatically inject a default route. You have to do the default information originate on the NSSA command in order to inject the default route. All of the other routing protocols inject, or all the other special area types inject the default route by default. All right. But yeah, we would treat, in this particular case, area 3 as that special use case. It would be a totally not so stubby area. And then we would basically, it would look like the rest of the areas. The only difference is we would have, in this particular case, we would have type 7s coming in, right? The 7s would be coming in here. These would be our area border routers, so those would become type 5s. We can still do summarization there. Remember, because we can summarize on an ASBR and we can also summarize on our ABRs. We can only summarize the 1s and 2s on the ABR. So this is our area 0. This is our area, we'll just call it 3 in this case because it's branch 3. All right, so that would work out pretty well. Let's see, the next task here, implement summarization. We'll analyze the summarization of the OSPF routes. It's like a fist punching something. So we've already decided that we're going to extend area 0 to each of the, essentially the border nodes of each of the branches. So that big fist looking thing is going to be area 0. Right? These are going to be ABRs. That's where we're going to be doing our summarization. And these will be area X depending on the branch. So area 2, area 3, area N, area 4, whatever. Makes sense. All right. At which points in the network will you implement OSPF route summarization within the backbone? Not even possible. You cannot summarize within the backbone because you have to do it on an ABR. Within the areas, at the area border routers. So summarization, of course, has to occur at only one location, and that is at the area border router. In OSPF, summarization within an area is not an option because it is a link state routing protocol. Everybody inside of an area has to have the exact same topology. You will summarize the stub area routers at the area border routers. Therefore, the stub areas will advertise a summary for all the networks in the area into the backbone. The stub areas will receive only the default route from the backbone so that summarization in that direction is not an issue. Because again, there's only one way in and one way out. That's the whole point of creating this stub area design. Summarization can also be done at the ASBR, where the EIGRP type 7 routes get injected into the OSPF domain. What are the migration steps? This is an interesting concept, right? We're running RIP version 2 across the entire domain, with the exception of EIGRP being redistributed into RIP version 2. The issue that we have is that RIP version 2 has a default administrative distance of 120. OSPF has an administrative distance of 110. So as soon as we start implementing OSPF, OSPF is going to become the preferred protocol. But is this really an issue? Let's say that I've decided to run both OSPF and RIP at the headquarters location. So I'm only really technically learning routes through RIP at this point because the branch routers aren't running OSPF yet. Is this going to be a problem? No, it's not going to be a problem because I can still use the RIP routes for reachability. As I start to convert each of the branch locations, branch 1 converted to OSPF, OSPF is going to become the preferred protocol because of administrative distance. Both protocols are advertising the same prefix information, assuming that we're running RIP version 2 in a classless manner. But the OSPF prefixes are going to be preferred because of administrative distance. We would still have reachability to branch 2, branch 3, and branch N, the other branches, because the RIP routes would still exist. So actually the migration would be relatively simple. Implement OSPF at the headquarters location, and then start to implement OSPF at each branch location. Once all of the branch locations have been incorporated into OSPF, then we can go and remove our RIP configuration. Let's see what they say here. When migrating from RIP version 2 to OSPF, you will implement a gradual migration or a cutover. What I was describing was a gradual migration. Cutover would be take out RIP version 2, implement OSPF in one kind of configuration. So do we deploy area 0 first or the stub areas? Well, it makes sense that we would deploy area 0 first because as we do this gradual migration, I would want more and more of the OSPF areas to be incorporated. If I do the area 0 last, I suppose you could do that because then you would have this kind of one instance where everything starts working. You would have kind of these islands of OSPF on the branch locations, and OSPF basically wouldn't be doing anything. But I think I would like it the other way, only because I would like to see that the convergence is working rather than having to troubleshoot the entire design. I can troubleshoot as I bring each branch online. I can verify the functionality of OSPF as I bring each branch online. Again, I don't have to worry about doing redistribution because we still have the RIP network deployed. So if I'm not learning the routes through OSPF, I will still be learning the routes and the destinations through RIP. Do we migrate the branches one by one or do a cutover of once and everything? Why do you need route redistribution between OSPF and RIP version 2? I would say you actually don't. How will the administrative distance of the routing protocols influence the migration? All right. The preferred way of executing the migration from RIP version 2 to OSPF is to do it gradually to avoid any lost traffic or network downtime. That's all they told us? Okay. Well, thankfully, I gave you guys a lot more information. Again, just because we're learning routes via RIP doesn't mean they're not usable. Eventually, as we start to add more and more branches and we configure more and more branches, those RIP routes will get replaced by OSPF. And then once we've confirmed the entire operation of OSPF, we can go back and then remove that ridiculous routing protocol RIP from the topology. But do we need redistribution? In this task, you're going to analyze the implementation of redistribution between Ospf and RIP version 2 during the migration. During the gradual migration, you will implement route redistribution between Ospf and RIP version 2. This is for Ospf segments to be able to communicate with the RIP version 2 segments that are not yet migrated. I could see that, yes. Because if you think about it, it depends on if it's a traditional hub and spoke or if it is, and in this case, I think it is a traditional hub and spoke, which means that the branches would still have to be aware of the other branches in the topology. But think about this for a second. I don't think you would need it. All right, let's walk through the scenario. Assuming that we're doing the summarization and everything as part of our Ospf implementation. So let's assume we're just running RIP version 2 and we've got our entire topology here. Branch 1 knows how to reach the other branch destinations because we've probably disabled split horizon and all those networks that are being advertised to HQ are being advertised to the other branches. Okay. But we already determined that when we move to Ospf, that we're going to inject the default route to the branch locations. So I'm running RIP version 2 at the headquarters location. I'm running RIP here, and I'm running Ospf. All right, that was step 1, implement Ospf at the headquarter location. If I go to the branch and I convert branch 1 to Ospf, right? Let's say I leave RIP in place. Whatever routes I learn through Ospf will have an administrative distance of 110. We've already decided that's going to be the quad 0 route, right? And of course, branch 1 is going to be advertising summary routes to HQ. So I think the argument that Cisco is trying to make in this is that when I do that, I'm going to lose that reachability information to the other branch locations. Remember, we're only running Ospf on HQ and branch 1 at this point. But would I lose reachability to branch 2, branch 3, and the rest of the branches? Well, from branch 1's perspective, no, because we have a default route. So we know that branch 1 thinks it basically can get to everybody. It may not have that detailed visibility because we are running Ospf. Actually, it would. I'll explain why in a second. But let's assume we don't have that detailed visibility of all the different prefixes that exist everywhere else. We at least have the default route. So we can assume that the traffic is going to get to the HQ location. HQ is still running RIP and Ospf. So it's going to have a bunch of RIP routes in the database for these branch locations. I don't see that there's any need to redistribute RIP into Ospf for that purpose, as long as we have reachability. Now, there is one downside to this approach, to doing this migration. If RIP still exists on this router, and we have to assume that we're not doing redistribution with RIP, if RIP exists on this router, we're going to have a bunch of RIP routes for those destinations, for all of these branch destinations, that are going to have a longer prefix length than, say, the default route, 28/24, right? So those RIP routes are going to have a longer prefix, which means that the RIP routes are still going to be preferred over this Ospf default route. But we would still have reachability. We would still have the ability to reach those destinations. So as long as we're running both routing protocols, I don't think redistribution would be necessary. I'm just trying to think of a scenario where it would be. Certainly Cisco is trying to suggest that redistribution is something that we would have to do based on how they document the case study, but I just don't see it as a need. Because we're still going to have the default route at the branch locations based on the fact that we've configured that as a totally stubby area. It's going to get a default route anyway on the ABR, and then the default route is going to also come from HQ. So maybe I'm missing something, but I don't see why we would have to do that. Right? And their justification, only the branch is fully migrated to OSPF, but it must be allowed to communicate to the other branches. We didn't get rid of RIP. If we said, you know what, let's tear down RIP completely, get rid of RIP at all the branch locations and start to migrate to OSPF, I would say, well, yeah, in that case, we would lose connectivity anyway, wouldn't we? We wouldn't even have the option to do redistribution. So my argument is that redistribution wouldn't be necessary, because if I'm not learning the route through OSPF, I would still be learning the route through RIP, because RIP is still running on all of our devices. All right. And by the way, redistribution would just complicate things anyway. Why would I want to add redistribution? You know, we have the potential of having suboptimal paths, not in this case because we only have a single path, but redistribution should be done at both the hub routers in a way that OSPF routes will be redistributed into RIP only. When the branch migrates to OSPF, the prefixes of this branch will not be seen in the rest of the RIP network because of the lower AD. Ah, you know what? I am thinking about this. I don't agree with that statement. I was gonna say yes, I understand what they're saying in this case. I've been thinking about this from the perspective of leaving branch 1, right? Getting from branch 1 to the other branches. What they're talking about here is that they're talking about the other branches being able to get to this branch. When a branch migrates to OSPF, the prefixes of that branch will not be seen in the rest of the RIP network because of the lower OSPF AD. I'm trying to think of, that would probably be an issue on the HQ side. It wouldn't be an issue on the branch side. And so they're exactly right here, because what's going to end up happening in this case, let me go back to this diagram, is once I do this migration, if I can stop there, once I do this migration, based on the assumption that they're not doing summarization in RIP, because they mentioned that the network is set up for summarization, they don't really mention whether or not they are doing summarization for RIP or not. But let me walk through both scenarios. So we've decided to implement OSPF here and here. So let's just say it's a summary prefix of X is being advertised. And that summary prefix is being advertised in both RIP and OSPF. All right. And this is a really important concept, because if RIP is not doing summaries and OSPF is, then we don't have to do redistribution. If RIP is doing summaries and OSPF is, then we would have to do redistribution. And here's the reason why. Let's say both RIP and OSPF are sending in a /23, a summary. Okay. Obviously, the only route that's going to end up going into the routing table of the company HQ routers is the OSPF route because it has an administrative distance of 110, which means that the RIP summary route, even though it's in the database, would not be sent to the other branch locations. So as soon as I implemented OSPF, these branches would no longer be reaching or hearing about that RIP summary that's being sent by branch number 1. However, if OSPF is sending in a summary and RIP is not summarizing, sorry, I had to cough there. If OSPF is sending in a summary and RIP is not summarizing, RIP is just sending in the regular networks, it wouldn't be an issue, right? So let's say there's 3/24s here. That's supposed to be a 4 and another one. So if those are RIP routes and those are being sent in, the /24s would still exist in RIP and the /23 would exist in OSPF. They would all go in the routing table basically because they're not the same prefix length. So I think based on how they're describing this scenario, we have to assume that RIP is doing summarization and the RIP route would look the same as the OSPF route. And in that particular case, yes, you would have to redistribute, but you would only have to redistribute at the headquarters location into the RIP domain so that that OSPF summary that's now being received and being used, that OSPF /23 or whatever it is that's coming from branch, would then get redistributed into RIP and we would still be able to see that in the RIP domain. Interesting. So we'd have to kind of make a couple of assumptions. They didn't really give us enough information in this case to really make that decision, but you kind of have to infer, how it's configured based on the fact that they're saying, hey, we're going to lose that route. And it would make sense that we would lose that route based on what I just described. All right. Redistribution should only be done at the hub routers in a way that the OSPF routes will be redistributed into RIP. There's no reason to go the other way because, again, we're still running RIP on branch 1. So those routes from the other branches would be learned through RIP, not through OSPF, because RIP is still running natively. When the branch migrates to OSPF, the prefixes of this branch will not be seen in the rest of the network because of the lower AD, again, assuming it's the same prefix length, until redistribution of the OSPF to RIP version 2 occurs. Redistribution from RIP to OSPF will not be required because the OSPF migrated branches will have a default route to the hub and they'll hold the complete OSPF and RIP routing information. We talked about that previously. Right? I mean, even if I didn't have all of the information, all the routing information, I could still use the default route to do that routing. So we would do each branch step by step, set them up as totally stubby or totally not so stubby. And implement that redistribution at the HQ location. Finally, we can then remove the RIP configuration. Will disabling RIP on the routers cause any routing table changes and or network downtime? Well, it depends. Did we finish the migration on the other routers? If we finish the migration on the other routers, there's no point in even running RIP. RIP doesn't play a role because RIP has an administrative distance of 120 and OSPF has an administrative distance of 110. So even though we're taking up resources and periodically sending out RIP updates and so on, it's not going to matter. because we're not actually using those routes. RIP version 2 can be completely removed from the configurations of all the routers once all the branches have been migrated to OSPF. All the routes in the routing tables of all routers will be OSPF routes because of the lower OSPF AD. Because RIP version 2 doesn't play an active role at this point, there is no relevant RIP routes in the routing table. Shutting it down will not influence the routing to those destinations. Fair enough, makes sense. In this last and final task, you will review the future growth of the network load at the hub routers. The hub routers at the company headquarters will maintain many adjacencies, mainly with the branch routers, right? What will you recommend to the customer if the number of adjacencies becomes a burden on the hub routers and the network operation suffers as a result? Since area 0, in this case, kind of extends down to the branch, adding an extra hub router really, I think, would be the best option here. Because it would still be part of the backbone, right? Let's see what they say here. Excessive backbone growth can cause issues in any network, but the number of adjacencies on a single router can be a problem that manifests itself a lot sooner and needs to be addressed. Because the Area 0 design is not easy to change in this scenario because of all the restrictions that we have with summarization, etc. Adding an extra hub router is the best solution to lower or maintain the number of adjacencies per router. Other Area 0 routers and branch routers are not at risk of high adjacency numbers because they each will have only a handful of neighbors inside of Area 0. Splitting load across multiple hub routers will will help the overall OSPF operation. I mean, generally that should be a good recommendation anyway, right? Because we want to make sure that we have the ability to ensure, redundancy and resiliency. So I would argue that we would want to have multiple hub routers anyway to share those redundancies, to share those adjacencies in the event that one of those routers fails. Okay? So that is it for this design scenario. We'll go ahead and wrap this up, and now we're going to get into the border gateway protocol.